那个麦克风吗？
刚刚有句话说的话，在hidden order 之间，selective magnet。
Is this on? Okay, it's good. So 没有回声呢。啊。So let's continue. So the afternoon one is about detecting of hidden order in Fluxural magnets. So the talk is specific to Fluxural magnet, but the idea can be quite general. Apply broadly to other systems. So so this work is mostly in collaboration with Chen Liu sitting in the audience, and also Yao Dongli, who is now a grad student transferred to UC Santa Barbara working with Matthew Fisher. So the outline is as follows. So first, I'll give some very, very simple nomenclature introduction to hidden order in condensed matter physics, and then to go to this specific context of rare earth magnets and introduce the idea of hidden orders with the intertwined multipolar order structure in this kind of system. So in the third part, this is in a collaboration with the experimental group in Fudan, with Yao Shen, who is a grad student of Jun Zhao, who is a professor at Fudan University. So explain the discovery of intertwined multipolar order in this system. So the references are here. So two theoretical references are already published, and this one is particularly nice. It's a long paper with a lot of details being written in this paper. So the experimental exterior collaboration is in this work. It's on archive this month. Yeah. So here things are very simple. There is no field theory, no exotic phenomenon, no fractionalization, no topology. Everything is simple. There's nothing like that. And I'm not going to use any of this language in this talk. So no topology, no fractionalization, no field theory, no exotic phenomena. So yeah, here you go. So yeah, so what's hidden order? So hidden order, this name occur if you are familiar with the English literatures, this name appears in many different contexts. This is like human mind. When we see some kind of structure we don't really understand, some structure we never seen before, we just use this name, hidden order. It's a name that doesn't have much creativity or imagination. It's a name just you use it. It's also used to understand the structure of corruption, in the government. So there's some underlying hidden structure you don't know, in the hidden structure in the organization of arts. Right? Yeah. So this is a novel, hidden order. Some bestseller, the #1 international bestseller. Yeah. Some contact problem. All right, that's okay. It's okay. So turns to this hidden order in condensed matter physics. This name, or this specific name for hidden order in condensed matter physics, has been there for more than 3 decades.
I think this has been discussed for a very long time.
Yeah, more than 3 decades.
I remember since 12 years ago when I went to US, we discussed this stuff.
Yeah, it's more than 30 years ago. Probably older than us. Right? So probably younger than Professor Gu, maybe younger than you. So this so this was first proposed in this very famous compound, uranium, ruthenium, silicon. So this uranium here is not radioactive. So not all uranium isotopes are radioactive. This one is not. So apparently in this Los Alamos National Lab, they has a lot of uranium, so they can make this compound. So this is like a heavy forming type of compound, actinide. Actinide. So it's the 5F electrons. Okay. So ruthenium provides a conducting electron. So this is the metal. This material is a metal, but uranium provides some more like a localized, almost a localized moment. So this is a phase diagram, experimental phase diagram, and this is the structure. Yeah. So this is uranium, ruthenium, silicon. They form this three-dimensional lattice. So this is a temperature pressure plot. So temperature pressure plot. Yeah. So this is the temperature pressure plot. So at high temperature, above like 17 Kelvin, there's nothing interesting. It's paramagnetic, nothing. At low temperature and low pressure, there's a hidden order appears. Now let me explain why it's hidden order later. So at a very, very low temperature, like order of 1 Kelvin, then you see activity emerge at very low temperature. So at high pressure, so the system actually goes to an uniform magnetic order at high pressure. So the system, because it has local moment, it has a uniform magnetic order. So why this green region? Yeah.要不要充个电啊什么？ It's a contact problem.
对，可能接触问题。没道理，你看你是随着。先不要动它，看看什么时候，是不是现在好？
那不要动它。
啊，不去碰它。
不要动它，对。嗯。So why this thing is hidden order? So I didn't show all the experimental data. So as you go from high temperature paramagnetic phase to a low temperature hidden order phase across the 70 Kelvin phase transition. So the first signature in the experiment would be there is a sharp peak, then the lambda transition peak, at this temperature. So yes, specific heat. There is a sharp jump of entropy. No, I'm not sure it's first order continuous. So the thing is, there is a huge entropy loss across the phase transition, right? So the huge entropy loss. So that means a lot of degrees of freedom are frozen. They form some kind of order, because entropically it's there.
The peak is very sharp.
Yeah. So this is a phase transition. This is a phase transition. So there is a loss of entropy. Yeah. There is I don't know. I don't know. It's periodically driven. Okay. So across this phase transition, there is a huge drop of entropy. And people don't really know where the entropy went, right? So entropy has to go somewhere, but it's not obvious where the entropy, disappear. So it's different from this phase transition. If you go to the high pressure, so you from paramagnetic to uniform magnetic order. So there is a drop of entropy. That where the entropy goes, the system just orders. The system develops long range order. This long range order corresponding to expands the nature of phase transition, expand the underlying structure in this ordered phase, right? But in this region, apparently the system become more ordered because of the loss of entropy. But we don't really know precisely what this, where the order has gone. What's the nature of the order? So that's why this is why it's called a hidden order. So.
周期性的频道，是它才黑掉，屏幕没黑掉。
屏幕没有黑掉。
看看接触。
Yeah, I don't understand hidden this pseudo gap. So people don't know it's what's the original around 2000 people proposed this may be a Z2 topological order. So maybe that's a hidden order. I don't know. And also this zero gap, if you go down from high temperature to low temperature, then it's not really a Phys transition. Then it's just a close collision, right? No, there is a Phys transition here. There is a Phys transition here. The Phys diagram, yeah, you are saying for this for the semiconductor Phys diagram, that's the opposite, right? As any for yeah.
But the key is that there is no significant loss of entropy.
Yeah.
When you go to the so-called T star,
Yeah.
so get temperature. But this one is a very sharp transition. That's the
Yeah, yeah, yeah.
go. I have to teach you.
Okay.
Sorry.
Thanks. Yeah. Yeah. So yeah, there is a second order transition at around 70 Kelvin. There is a loss of entropy, which is about 40% of some spin 1/2 like diffusive freedom. Yeah. This thing is not really functioning well. Yeah. Yeah. So yeah, this is also called dark matter incandescent matter. So apparently the system ordered in some way, some fashion, but we don't know what type of order underlies this Phys transition. Right? This is a different. Shoot, that's what causing this. 等一下，我要把它再插进去也行。
主要是这根线，
哪根线？
点这个投影仪的问题。
这是投影仪的，这是投影仪的是吧？
对，这个投影仪的。
那再把它再插一下也行。可以了，就不管它，看它怎么样。行。好。好，就是这样嘛，看看它最后怎么样。这跟直播也没什么关系嘛，这就是这个屏幕的问题。对。So that's the so the order parameter associated with this hidden order is really unknown after decades. The reason it's not obvious what kind of order this hidden order is because this underlying order does not couple directly to the experimental probe that we used to. No, it doesn't couple to magnetization, so you don't see any signature of magnetization. You do neutron scattering measurement, you do X-ray, you don't see any structure signatures of this underlying order, right? So then, how do we, find or confirm the existence of the precise nature of this hidden order, right? So that question is quite obvious. Like this is 3 decades of question, 3 decades of puzzle in condensed matter physics. Is there any idea or any?
If a second order transition, how can a specific heat has such a sharp peak? Shouldn't be like a.
It's a lambda peak. It's a lambda peak.
Oh, lambda peak.
It's a lambda peak, right? Okay. Second order transition. Yeah. So then there are various proposals, and this once this hidden order was proposed, there are a lot of proposals of hidden order in other systems, right? So anything we don't really understand or hidden, not always coupled to any experimental probes are named after hidden order. So there are candidates like a magnetic multipolar order, electron multipolar order, even some orbital order. The important question: how do you reveal these hidden orders? Actually, in this context, in the uranium ruthenium silicon, so the hidden order was suggested to be some kind of electron multipolar order.
So which item carries the spin, the magnetic moment?
Well, uranium would carry magnetism because pretty localized, but it will hybridize with ruthenium d electron in some fashion.
So spin 3 half or spin 2 half?
No, so uranium is 5F. So it's nearly itinerant, but it's localized. There is a condo-like coupling going on here. Yeah, your advisor is probably more expert in the field of this. Yeah, so yeah, that's the introduction on the hidden orders. Let me switch to a concrete context of rare earth triangle lattice magnets. Yeah, yeah. So what's the rare earth? Yeah, I mean, among last 2 or 3 years, we have a very nice collaboration with a bunch of experimentalists, including Chen Zhang from the Ming University. So he's an experimentalist, grow various materials. So their group found this material called ytterbium magnesium gallium arsenide. So in this material, ytterbium, which is the rare earth atom, they form a triangle lattice of this type. It's a perfect triangle lattice, and this red atom is a triangle lattice. They're very separated. The distance between these layers are much larger than the intralayer distance. So it's a perfect two-dimensional system. It's a two-dimensional system, so with a two-dimensional local moment. It's a motor insulator, essentially. So I don't want to get into details of this compound. It turns out that this thing was proposed by us as a candidate for spin liquids. It's a very nice candidate for spin liquids. It has attracted a lot of attention worldwide. A worldwide interest in this system and the physics alike, physics related to this system. So, yeah. But I want to point out this kind of this material is not alone. In a sense, there are lots of isostructure material. Because all these rare earths have similar chemical property. Moreover, there are lots of other, rare earth triangular magnets of this kind. You can replace rare earths with any other rare earth atoms. Replace uranium, gadolinium, terbium, dipole-octupole, holmium, erbium, deuterium, ytterbium, right? So you can replace all of them. You can obtain similar type of Hamiltonian with similar type of, almost similar type of local moments, right? So there are lots of games, one can play. A lot of rich ground, to explore the physics, right? Yeah. So it turns out, as I said, there are any kind of rare earths on a triangle lattice in a D3 dipole group. One can propose some generic Hamiltonian for them. So Chang, Liu, and me and Yao Dong, we wrote down this table, a full table that lists all possible relevant spin Hamiltonians for the local moment physics in governing the magnetism in the rare earth triangle lattice system. Yeah, so this is a table illustrates is a complete modeling of the interaction. Yeah. Yeah, so the rare earth 4f electron are pretty localized. So one do not usually worry about further neighbors. Occasionally one worry about that, like a dipolar interaction that's longer ranged. Right? Usually we don't worry about it. We only consider first neighbor. And yeah, this is a complete list of them. Yeah. So there are the so-called dipole, octupole, and usual Kramers doublet and non-Kramers doublet. And this guy applies to ytterbium. Yeah, it's not really. Okay, Xin. Let's continue. Yeah. So what's the non-Kramers doublet, right? So you have even number electron per site. This is not just applied to this presidium 3+ listed here. It also applies to terbium. Excuse me. So terbium are other elements. So this guy has a 9-fold degeneracy on the 9-fold degeneracy on a 9-fold degeneracy on a crystal, like a D3D point group. It was split into multiple doublets and singlets. It turns out the ground state one is a non-Kramer doublet. So the protection is not due to time reversal, it's due to lattice point group symmetry. So because of that, yeah, so the effective model describing the interaction between these local moments is a highly anisotropic one. It has both the XXZ part and bond-dependent. This is complex, right? So this gamma ij is a bond-dependent Phys variable. So it takes different values from these 3 different bonds, right? Yeah, why is that? Why there is this funny, bond dependence, right? So this local moment, it's not a pure spin local moment. It's an entangled object of spin and orbitals. It's not a pure spin, or not pure orbital. It has a spin part and orbital part, right? It's an entangled, quantum mechanical entangled object of spin and orbitals, right? Because orbitals are involved, so orbital has orientation, right? Orbital has orientation. Spin is operating in its own Hilbert space. It's an internal spin space, but the orbital are real. Orbital has a real spatial orientation, right? So as a result, because of this spin-orbit entanglement, so the orbital orientation will be inherited, right, by this spin-orbit entangled local moment. So this spin-orbit entangled local moment will have an orbital character. As a result, the interaction between these local moments will depend on orientation of the bond, because the orbital has orientation, right? So that's why this effective interaction between the local moments depends on the orientation of the bond. Depends on the orientation of the bond.
Is this a generic feature for all the SOC coupling?
Is a generic feature for what?
For all the spin-orbital coupling, you have this.
Yeah, it's a generic. This is general. Yeah, but it's general, but the particular form of the interaction will depends on the nature of the local moment. Yeah. Yeah. Yeah.
So this is like an XYZ model plus something, plus some additional term.
XXZ model XXZ.
Oh yeah, I can do
yeah.
Get it plus.
Yeah, plus the actual term. Yeah.
This is
Yeah.
so I think it's an XYZ model.
XXZ model.
Total is XYZ model.
No, this is not. Only the phase when this phase is 1,
Because
that's XYZ. Yeah. When this phase all vanishing, that's XYZ.
yeah.
Yeah. Yeah. So another important feature of this model is there is no closing term between SZ and the transport term, because they have different property under time reversal symmetry. Yeah. So they are time reversal symmetry forbids the coupling between the Z component and the transport component. Yeah, there's no such a mixing term. That's an important element due to time reversal invariance. Yeah, under time reversal symmetry, SZ changes sign. The transport component do not, right? So if imagine you have SX SZ term, on the time reversal symmetry it will become minus SX SZ. So such a term is forbidden by time reversal symmetry and homotheticity together. Yeah. Yeah. So yeah, I want to make another point, a little bit deviate from the main topic. So people, if you want to read about archive, which I'm not really don't enjoy reading, so you may every day, every couple of days, you may see some title with Kitaev, right? So Kitaev Heisenberg model, ruthenium trichloride, Kitaev spin liquid, right? Kitaev spin chain maybe. So this is people interested in people propose this people study this 5D for the transition metal like iridates, leucinates, leucinium trichloride. Try to understand the presence of K-type interaction. Try to understand if the K-type spin liquid can be realized or not. Yeah. So K-type spin liquid was actually first proposed by K-type around 2003. The paper was published in 2003. Probably he obtained the result much earlier. He wrote down this exact model, exact submodel called the K-type model on honeycomb lattice. Yeah, the people know this. How many of you have ever heard about the K-type model on honeycomb lattice?
It doesn't matter.
So if you heard about it, raise your hand. None of them. Okay, maybe it takes some 5 minutes to blackboard the introduction to K-type. Yeah. To K-type honeycomb lattice. Yeah. Get the eraser. So it's K-type. And physics. So yeah, so here first there are so-called K-type honeycomb. This really means honeycomb K-type model. There is only a version which is a K-type toric code model. So he consider honeycomb lattice. Yeah. So cause this z x y, z x y. Yeah. Yeah. So the model he wrote down is this. Yeah. Yeah. So what does this mean? So mu equal to x y z. So when mu equal to x, it really means this bond. So this will be sx with the coupling jx. So for x bond, for I j belong to x bond. So the Hamiltonian would be jx, sx, sx. For ij belong to y bond. That's jy, sy, sy, sy. Right? For ij belong to z bond. So this is jz, sz, sz. Right? So it's a pairwise spin interaction. But the interaction is dependent on the bond.
But apparently this model cannot exist in any material.
No.
Possible, how can it be, purely because along this direction as third direction?
Yeah, so so yes or no, right? So no means it cannot be precisely realized.
In realized, you need to add has more term, right?
It has more term, yeah. My answer is yes or no, right? Yes means this term can be realized. The Hamiltonian can have this kind of term, right?
Well, it depends because it depends on how you factorize the Hamiltonian form. You can write down like any like SYD model, and you can also factorize such.
Yeah. So that's a good point. Yeah. So but the thing is, what I'm going to emphasize has never been emphasized by others is any lattice, with a threefold rotational symmetry, like this one. So there is a threefold rotational center, which is this one. So there is a C3 rotation. Around this axis, you can rotate by 120 degrees. The system is invariant, right? So any kind of system, motor insulator, for instance, a spin-off with strong spin-off coupled the motor insulator. If you have threefold rotational symmetry, like C3, you would necessarily have a kitab term in the Hamiltonian.
But you never know the leftover term whether it's relevant or irrelevant. They may compete for all of these features discussed actually, because it's a 2D.
No, so the thing is, to have kitab spin liquid, you have to have the term to be dominant. Yeah, to be large enough.
No one can prove that actually so far. I also searched read many literature about it. No one really proved that the additional term, how it might affect these other features.
Yeah, so as long as additional term is not large enough. Yeah, because spin liquid. No, this is 2D. Kitab spin liquid is robust against any local perturbation.
I don't believe it.
So the spin liquid is a. So there are two spin liquids first in here. So usually it's labeled by a Phys diagram of this type. It's solved exactly by adjacency type. So yeah. So the isotropic point would be when Jx, Jy, Jz are equal. It will be in the center of this triangle. If Jx is dominant, it will be this region. Jy is dominant this region. Jz is dominant this region. So this white region is gapless. So it's called a gapless kitab spin liquid. It's a critical spin liquid, quantum spin liquid. This is gapped Z2 spin liquid, quantum spin liquid. And these regions can be mapped into the previous model by Kitaev called the toric model. So this can be described by, or this effective Hamiltonian can be described by toric code. It's an exact solvable model for Z2 quantum spin liquid. So this is also a Z2 topological order. So Z2 spin liquid is with a fully gapped spectrum is a Z2 topological phase. So it's robust against any local perturbation. So if your actual perturbation from other interactions is not significant enough, so the system is still in the same phase.
How about magnetic perturbation? If you can like apply strong field coupled to like a certain spin direction, and then you can also introduce a perturbation term.
Yeah, any local interaction.
But if this field is strong enough to close the gap, then.
Yeah, strong enough then it doesn't work.
Yeah.
If it is weak, so it doesn't matter.
Yeah, gapless. But if it's gapless.
For gapless, if you apply field, you get a gapped kitab spin liquid. There's a chiral spin liquid. There's edge states. That was big. There's a big excitement right now about the observation of quantized enormous Hall thermal Hall transport measurement in the ruthenium trichloride. They seem to suggest that there is a chiral Majorana modes on the edge due to the presence of due to the opening of a gap in the spectrum of this gapless kitab spin liquid. Yeah, so that's roughly the introduction, right? So this is the model, and this is the model he wrote down by Kitaev wrote down as the toy model. He want to try to provide a general theory for topological order, how to understand the symmetry and the topological order. So he used this as the example, but this example can potentially be relevant for a real physical system. It was pointed out by George Jackley and Kalilin, right? So 2000, I think it was 2009. This PIL paper by George Jackley and Kalilin, Yes. This is from German group. So let's study iridate, honeycomb iridates in the context of honeycomb iridate. Told us this may be a realistic Hamiltonian, can be relevant for real physical system. Yeah. So this is for 5D transition metal. Iridium is 5D transition metal really because of spin-orbit coupling. The spin-orbit coupling created this effectively J equal to 1/2, which we explained for this pristine iridate yesterday. So this creates a spin-orbit entangled J equal to 1/2 states. So we don't need to worry about too narrow outside to this 5D or 4D transition metal. What's important? What's the crucial element to generate K-type interaction is spin-orbit coupling or spin-orbit entanglement, right? As I said, any threefold rotational symmetry on a lattice, on a two-dimensional lattice or three-dimensional lattice, for spin-orbit entangled, spin-orbit coupled motor insulator. Remember this sentence. So for any spin-orbit coupled motor insulator, if there is threefold rotational symmetry, then there must be a K-type interaction there. So this is the sentence we wrote in our paper. So if you have a threefold rotation like this, you do a rotation, do a threefold rotation. What do? You permute Sx, Sy, Sz. If you define your Xx, Sy, Z this fashion, people understand what I'm talking about. So yeah, if you have some visualization of the lattice, see rather, wait, rather. That's okay. Yeah. If you have a three-dimensional lattice, and this is the how do you visualize this? Imagine this is a cube, right? And this is one direction. That's the threefold axis, right? And you define x, y, z this fashion, right? So what you do, you're doing rotation around this in the diagonal direction. What you do is you are permuting this three axes, right? You rotate by 120 degrees, you are permuting this x, y, z. You're permuting x and y, z, right? X to y to z to x, right? And if you define your spin variable, if you define your spin in this coordinate basis, what you do is you are permuting Sx, Sy, Sz, right? So in order to have a Hamiltonian to be invariant under this symmetry operation, you necessarily have a K-type term in the Hamiltonian to have terms like this along x bond for along x bond Sy, Sy, Sz, Sz. So when you do the rotation, when you do this threefold rotation, you are rotating this bond to this bond to this bond. At the same time, you are rotating the spin component, right? If the system do not have spin-orbit coupling, you do a rotation and you do a lattice rotation, and you don't affect the spin component. The spin symmetry and lattice symmetry are independent. If there is no spin-orbit coupling, they're not locked. In the case of in a system with spin-orbit coupling or with spin-orbit entanglement, the spatial symmetry and spin symmetry are locked, right? When you do a rotation, you are rotating the lattice. At the same time, you are rotating the spin in a reverse fashion, right? This is why we learn in quantum mechanics. Spin is the pseudo vector. You're rotating the lattice. At the same time, you are rotating the spin in a reverse fashion. So that's actually the key reason why spin-orbit coupled motor insulator with threefold rotation can fundamentally have a K-type term. So this is if one see that, so then we can go beyond the original proposal of 4D, 5D iridates or lucinates. So the key important information is spin-orbit coupling or spin-orbit entanglement. So what kind of material can have a better spin-orbit entanglement? Certainly much heavier atom would be better. So rare earth, 4f electron is certainly much better than 5D or 4D electrons, right? These rare earths are much heavier. The spin-orbit coupling is actually dominant energy scale in the problem. So you don't even, also the 4f electrons are much localized. So you don't worry about further neighbor couplings. So the interaction is mostly like short-ranged, the fourth neighbor. So in that sense, these rare earth-based magnets can be a much better Kitab material than these 45D elements. So that's the proposal that explained by Phys and my former student Yao Dong and us in a paper in 2016, 2 years ago. So that basically tells you the point, proposes the idea that vast families of rare earth magnets, especially rare earth honeycomb lattice, may host this Kitab physics.
The problem is that no one really knows the ground state of Hamiltonian right now. Right?
Yeah, we don't care. So
like also the physics, the ground state also change actually. You don't know actually how you change.
yeah, so you can ask experimentalists.
No, I suppose it can only provide you some evidence, and that doesn't mean.
Yeah, so this is just step by step. This requires mutual feedback between theory and experiment. We taught the experiment, you look at these systems, and then they do the measurement and feedback to us. Then we make further effort to try to understand the experiment data. If it doesn't work, then we can find other compound.
This. Like why learn from the XZ model? If just fine-tuning the data just from data larger than 1 to data equal to 1 and data smaller than 1, just in this nearest neighbor region, the physics change a lot actually. So and here the change is just not by some tuning of K. It's also add many additional terms here.
Yeah, sure.
So it's hard to say it can still stick to the spin, this kind of ground state property.
Yeah.
It's very.
Yeah, but once the spin equator is there, it is there. Once it is not there, it's not there.
Okay.
Right? So once it's been realized, then you find some greater evidence that support the suggestion, right? Once it is not there, it's not there. I don't really.
Even there, you might not claim it is the same quantum spin liquid if they claim.
Yeah,
right?
yeah, that's a good point.
Yeah.
We are writing another paper.
Yeah.
We actually had another paper making this statement. Yeah, that's a good point. Yeah. And 6-fold, this is not 6-fold. So this actual lattice has a 3-fold rotation and inversion and C2 rotation. It's not C6. It's not C6. It's not C6. It's not. Yeah, the symmetry is lower than C6.
And also, there's also another question actually raised by me. Why they learn from U protocol? There are so many different kinds of discretized symmetry you can break into. Then how can you, exclude all of them in your theory?
No. So the thing is that we are not trying to explore all possibilities. We just want to find the most interesting ones. Yeah, there are different ways of doing physics, right? We don't need to explore all possibilities.
Yeah, I understand.
You just find the interesting ones.
Yeah. There's like a certain type of spin liquid, and then how can you exclude it from the other type of possibility? Right?
Yeah,
within the same model.
Sure. Yeah, finding one is the most important one. Then ask what type of. Here we are not just interested in spin liquid physics. I'm just trying to point out Kitab interaction is generically present. Is generically present in these rare earth magnets, and this point has never been made by any others. Which is, seems to us this is an obvious statement, but people did not realize that. So in the vast families of rare earth magnets, people never thought about the presence, never discussed along the lines of Kitab interaction. I thought this is a missing point. Sometimes all the whole community think this might be a great problem to work on, so that they step into that field and explore all kinds of possibilities. Maybe they're missing a lot of interesting things. People are working on this ruthenium trichloride, working on these honeycomb iridates. They invest lots of money, doing these rigs, doing this neutron scattering measurement, very, very low temperature transport measurement. This may be great, right? So there are other interesting things to point out. These people are missing the point that this Kitab interaction, Kitab physics can be important, can be relevant for these rare earth magnets, and these people do not even talk about this in the community, and we point out that there can be a great opportunity up there, right? If some experimenter really realize the significance of this point, So they make some small effort to try to doing some measurement and discuss the expandable phenomena along the lines of K-type interaction. That is going to be important eventually. So I just make a point and explicitly show for this looking Hamiltonian. For this Hamiltonian, which is obvious does not look like a K-type Hamiltonian at all if I write the Hamiltonian in this fashion. But if I transform the coordinate in this fashion, define my coordinate basis, define my spin basis as this one, rather than this and that, I use this as my spin coordinate. They are all 90 degree. So then the K-type term become explicit. Right?
So that we write Hamiltonian.
I rewrite the Hamiltonian.
The previous one just like a deformed XYZ model.
Yeah.
Defined XYZ model.
Yeah.
But generically, for any Hamiltonian with spin interaction, you can always factorize all this time. Right.
You could always write on anything in this. Yeah. So the thing is, there is a microscopic reason to support the emergence of this term. There is this. As I said, this threefold rotational symmetry of spin orbital entangled nature.
At this situation, it's more natural to factorize all this.
Yeah. They're orthogonal. They're all orthogonal. Let's define this one. No, this one. This is the XYZ direction. So this is the triangle plane. XYZ is defined this way. And this is Z direction. Original Z direction is normal to the plane. And this is the XYZ. Just like what I introduced here. Yeah, so the 1-1 plane, which is this plane, is the triangle lattice plane. Right? I define the new spin basis as this X, Y, Z. And this is the original Z direction for the normal to the plane, which is the 1-1 axis. Right? If we do threefold rotation, you are permitting X, Y, Z. Yeah, so this is the mean field Phys diagram obtained for the model, the model for the non-Kramers doublet. How do we understand how do we understand this rather complex looking Phys diagram? So along this axis, on this horizontal axis, there's a mean field. Everything here is a mean field. Yeah, it's okay. Yeah, no. For spin 1/2, on this axis, everything is understood. XZ model on a triangle lattice is for every parameter regime is very very understood. No, completely.
Impossible. There's no exact understanding for ground state.
No, this is not Heisenberg model.
This, even for this situation.
Yeah, for the triangle lattice Heisenberg model, we know it's a 120 degree state. It's the order the 120 degree state, right?
Oh, you mean okay? You mean ground state order?
Yeah.
I mean the ground state wave function.
Yeah, we're not interested in that. So we try to understand the nature of the ordering. So along this axis, everything is known. We know the system develop a magnetic order of some type, right? So away from this axis, when we turn on this anisotropic term, there are other phases. All these phases, when in this big region, this fx, stripe y, nail y, xy, these things are also known, because mean field theory doesn't find any kind of degeneracy. It uniquely find one ground state. So these are strong ordering tendencies. These are well ordered. So we know this describes the system. Only in the frustrated regime, when the ice interaction dominates, so then ice interaction on a triangle that is highly frustrated and it's huge degeneracy. The perturbation we add, the quantum perturbation like transverse xy and or the J plus pi term, this is not necessarily completely lift the degeneracy, but one can do mean field theory away from this x-axis limit. In the x-axis limit, because it has a global U1 symmetry, so x-axis model on a triangle lattice can be perfectly mapped into a helical boson, interacting helical bosons on the triangle lattice. So this model, as we know, in this region supports supersolid phase. It has both superfluid order parameter and density order parameter. So yeah, so this region, in the frustrated region, this region, it has both superfluidity and crystalline order.
Converting to in the spin language,
yeah, in the spin language, that's AFZ and FXY. So it has a ferromagnetic order in the XY plane and antiferromagnetic order in the Z direction. Yeah. Or on the other side is antiferromagnetic Z and FZXY. So away from this, we can doing this mean field calculation, find the other phases. So this looks like a completely trivial. Moreover, there is a property. This phase diagram is symmetric for positive J++ and negative J++. If we do a rotation around the z-axis by this degree, you can I think it's pi/2 rotation. It's probably typo. You can doing this. It should be pi/2, I think. Yeah.
Pseudo spin. If you apply 128 degree, because it's a protocol, it will actually itself.
Yeah, we can talk about this later. It's probably a typo, I think. So the point is the labeling of this phases looks like a trivial one. It's all ordered in some fashion. The way I was educated, like ordering is boring. That's how I was educated. Like any kind of ordering, we are getting very, very bored. So it's not always the case. Ordering can be interesting. So if we translate this language into if we translate the language
So I have a quick question. So Chen is from Renmin University.
he's a postdoc.
Oh,
Postdoc. Yeah. So this is a list of these orderings in terms of their physical properties. So as I said, this xy direction is all even on time velocity symmetry. The Ising component is odd on time velocity symmetry. So this transport component is actually a quadrupolar moment. It's not a multipolar moment. So if you are not familiar with this language, so you may learn that from electrodynamics. Electrodynamics. There is a multipolar expansion for the electrostatic potentials, right? So some kind of a volume or some charge, right, distributing on a small volume. Then you look at the potential energy mediated by these charges, a group of charges, right? So there are total charge. That's a summation of the total charge averaged over every place in the volume. There is this polarization. This is like the sum of this electric charge times the moment times the position. So the polarization would be proportional to density times the position, and doing a volume integration. That's the polarization. So that's the polarization. If you go to high order, that will be quadrupolar moment, right? Octupolar moment. There will be much complex average of the electron charge distribution in the space, right? So this is called the multipolar expansion of electrostatic potential of a static charge distribution in a space, right? likewise, in the spin system, you can define a similar kind of multipolar expansion for spin local spin moment, right? So we know in magnetism we don't really have magnetic monopole. We don't have electron charge, So magnetism will start from polarization, starts from electromagnetic polarization. So the magnetization would be just the magnetic polarization. But for more rich, Hilbert space, like a larger spin moment, which has a much richer Hilbert space, you will allows high order, multipolar moment. Like for spin 1 moment, we can have a quadrupolar moment. For spin 3/2 moment, we can even have higher, octupole moments. Yeah. For in this context, where the local moment is a J is the larger one. It has this multipolar moment in addition to the Ising component, the dipolar moment. So this Z component of the spin, Z component of the spin that normal to the triangular plane, is the Ising component is a dipolar component, and the transverse component is the quadrupolar component. There is even on the time reverse symmetry, right? So this fxy and the nail, 120 stripe y, these are all called pure quadrupole moment because of the ordering are in the xy plane. So these are pure quadrupole moment. And because the ordering occurs in this quadrupolar moment or this multipolar moment, it do not appear as a magnetic Brock peak because it does not break time reverse symmetry. It does not break time reverse symmetry. Neutron spin would not be sensitive to these orders because neutron spin coupled to the spin, coupled to magnetic order. So this is not a real, conventional magnetic order that breaks time reverse symmetry. This one does not break time reverse symmetry. So the neutron spin would not see it. So you would not see any, magnetic Brock peak in a neutron diffraction measurement, right? You will not see that, right? So the other three, the lower panel is called the intertwined multipolar order. It has both the Ising component order in the Z direction and quadrupolar order in the XY plane, right? It supports both the Ising order and the quadrupolar order at the same time, right? It's a mixed nature. The question?
So you use a 120 mu is a quadruple order?
Yeah, it's in the XY plane.
Yes, but I can measure the spin-spin correlation in the XY plane. I assume you still see some peak in your structure.
The thing is, you cannot measure that.
I mean, theoretically.
Theoretically, you can do that. Experimentally, you do not.
Quadrupolar or multipolar, that is a mathematical definition. I mean, if I have a linear, some kind of a linear operator can reduce it to 120 mu, also the stripe order, I would not call it a quadrupolar order.
No, I think no.
For all the multiple orders, they have some kind of internal symmetry. For this mu order and the stripe
Yeah.
order, they do not have this symmetry.
They have internal reasons. These are depends on where you start. How do you define internal, right? How do you define your internal? If I define internal in terms of J, if I write down everything in terms of J, which is let me go back. So if I define everything in terms of J, so this S would be obvious in this quadrupolar moment in J. So X, S, Y will be J squared, order of J squared at least, right? So that's J squared is even on time reverse symmetry. Is a quadrupolar moment in terms of J, right?
But J is just the parameter.
No, J is not a parameter. J is a real local moment. Yeah, J is a real moment, right? Yeah. So I describe everything in terms of observables. I'm not trying to, I describe everything in terms of physical observables. Yeah. So if you imagine you do a elastic neutron scattering measurement, yeah, if you do a elastic neutron scattering measurement, you don't see anything. Although specifically, if you do measure heat capacity, there is a TC, there is a phase transition. Now this is a two-dimensional system, and the symmetry is very low. It's a discrete symmetry. You have to have a finite temperature phase transition. So you would see a TC, there is a jump, there is a lambda phase transition, indicating there is an ordering occur. But if you do a usual magnetic measurement or neutron diffraction, μSR, NMR, you don't see anything. The magnetism, this hidden order, they cannot be recorded in a conventional magnetic measurement. It's hidden, right? So this is the pure quadrupole moment. In addition, there are intertwined multipolar moment. So both have this Ising component ordering and XY component ordering. So Ising component along z direction is the dipole moment, and XY component is a quadrupole moment. So if you do, like a NMR or μSR or neutron diffraction, you will see a black peak at the cap point. Now for NMR, you will see several peaks appears, indicating the emergence of internal, three different internal fields emerging due to the Ising component ordering. But that's not enough. That's not enough, because the transverse component of the spin also orders, and this the order you measure by neutron diffraction or NMR μSR cannot account the missing part. There is a missing part. The system ordered in the XY plane, but the order you measured by other measurement cannot account the complete ordering pattern, right? So this is what I call the intertwined order, right?
So this definition are not described to the model the previous component, but you reduce some general definition.
Say it again.
So these are some general definition, not described to the component you just showed.
So this one.
Yes. So
Yeah, this one is not generic. Oh, this is generic. This is generic, but this notion is specific to the model and the system. Yeah.
And so do you know, I will call this intertwined order, just some actual matrix of actual order. That's also with some fair mathematical definition. Some order perpendicular in the plane to the plane, and also some order in the plane.
So what's the intertwined order you define here? Are they similar as the one raised by Rebecca Flynn and Piers Coleman a few years ago? I remember there was
I think intertwined. This name was invented by Kiverson. Yeah, Kiverson was. These two operators, they do not commute, but they also order.
So you mean they reinvented?
Yeah, I don't know. This SX and SY, SD, they don't commute, right? They do not commute. Yeah, so some details by some calculation by Chang on some order by disorder phenomena. So now I want to explain how to detect these hidden orders. The idea is, I got 20 minutes maybe.
30 minutes.
Yeah. No, 1:30 to 20 minutes is enough.
Because there are many.
Yeah. So the idea is use a non-commutative observables to detect these hidden orders. Yeah, what does that mean, right? What does that mean? Yeah. So we can combine to detect the intertwined multipolar order. We can combine both elastic and inelastic neutron scattering measurement. So elastic measurement will directly see the underlying, dipole order. You have dipole order and for magnetic Fz, right? So you get a black peak at the cap point, right? But you cannot use this measurement, measure the result to account the complete ordering pattern, right? You cannot do that. There is a missing piece, right? So this missing piece, how do you reveal this missing piece? Missing piece in the quadrupolar channel, right? In the hidden order channel, right? So the idea is that you can use this non-commutative variable. So you're doing an inelastic measurement. Again, inelastic measurement, spin still coupled to z component of spin only. The neutron spin still coupled to z component because of time inverse symmetry. Only the z component of spin is magnetic. So the neutron spin would pick up this component. And you are measuring this spin correlation function of the z component, right? So even though you are not doing a polarized neutron scattering measurement, you are automatically picking up a z component of spin. You are automatically doing a polarized neutron scattering measurement. So you are measuring this z component correlation function. So what does this thing really represent? Right? It's a z component correlation function. So the observation is like as follows. So you are ordering in the xy plane. You have some ordering pattern in this xy plane. You have some structure, hidden order oriented in this complicated fashion. But how do you see it? So you are doing a dynamic measurement in the z direction, normal to the plane, right? So sz, they do not commute with this operator in this hidden order space. They are not commute. The quantum mechanics is not commute. So what you do is you apply sz on this one. You are creating a flipping event. You are creating a coherent spin excitation. Create a coherent excitation within the Hilbert space, within the Hilbert space of these hidden order parameters. So you are creating coherent excitation, and these coherent excitations are recorded by inelastic neutron scattering measurement. Okay? Yeah. So what this thing do is it reflects the dynamic, directly measure the dynamics, the coherent dynamics of these hidden orders, right? And this coherent excitation that recorded by index neutron directly reflect the underlying structure of the hidden order, right? So this is the idea. This is the proposal of selective measurement, right? So you do an elastic measurement. You are really measuring the elastic property. You are measuring the structure of this, Ising order, measuring the structure of the dipole order. But if you are doing an inelastic measurement, you are measuring the dynamics of the hidden order. Using this non-commutative, using this orthogonal observables. Yeah. So this is the prediction for the structure dynamic property for different phases. That is obtained by Changzhou and Yaodong for different phases. Yeah. So I don't want to get in detail, but there is an interesting selection law that was worked out by these guys. So they figure out there is a selection law such that, for instance, for the stripe Y, the system has two sublattices. In principle, you should see two branches of modes. But here you only see one because the stripe order already has a residual symmetry. And this residual symmetry will pick up one branch of the mode. So because you are only measuring the z component of spin correlation function, there is because of this selection, there is emergent selection rules out of the underlying symmetry of this stripe order. So you can only see half of it. So this is what they figure out. There is underlying symmetry, which they labeled by W. It's a combination of spin rotation and translation. So yeah. For the last remaining 10 some minutes, I will just give a brief introduction to a real experimental work. Sure.
You also compute the x-x correlation.
Yeah, you can compute that.
Did you do that?
No, this is not measurable.
Not measurable, but I want.
No, access is measurable. You can do transverse measurement. Actually, it's possible.
No, the neutron spin do not couple to the.
No. Like measure both. I'm sure you.
No.
Because my student is actually a Newton guy. We also have a comparison actually.
Yeah, it's different. It's I think for conventional magnet, if you do neutron measurement, you measure both the spin flipping event and the spin preserving event. So that will correspond to both the SSZ, SZ, SXX, or any kind of combination of spin correlation function. Here, because of the constraint of time reversal symmetry, You don't have that kind of property. If you write down microscopically how the neutron spin are coupled with the local moment, so the neutron spin would only couple to the z component of the spin because of the invariance of time motion symmetry. Yeah, what's the question in there?
So the x-x correlation, the x-x correlation, the low positive, expect to see some spectrum like the ZZ, or you expect to see nothing?
You will see some more things. You will see more things. For instance, you would not see, you would not have this kind of selection rule. You will see two branch, for instance.
Oh,
Yeah.
we can still see one branch which is hidden in the ZZ.
No, you will see more things. So you would see, for instance, so this is SZ flip the transverse component. If you measure SX, you will also flip the Ising component. So you will see the dynamics due to this presence of this Ising order. So you will see more things.
So maybe my question is like you will still see magnons in the XY plane.
You see magnons. These are all magnons. These are all magnons. In a precise sense, these are all magnons. These are all spin wave dispersion. These are ordered system.
The form methodology is spin wave.
Yeah.
Also in the XY plane, you assume we have like a quadruple order.
So in principle, I think they should also calculate the transverse response of neutron scattering. Because it's also measurable actually in reality. You can locate the neutron spin component along in XY plane. And then when you rotate it, you also couple to the local spin, and then you can also observe the response in this transverse direction. So
No, so
that's how we can do it.
no, yeah. So